Good afternoon. So I showed this picture. How many people saw this picture, the rear one? I think it's definitely people saw this, right? This is in Barcelona, and it's Gaudi's, beautiful thing. It's actually on top of a roof. These are chimneys. If you look at those beautiful girls, these are actually all geometry. If you look at every shape is geometry. So it is really mass, finally integrated into beauty. Okay, so I'm showing this simply says I went down there, actually gave a keynote speech for the ECML PKDD last year. It's on information networks. Okay, but since this time Nashir asked me to set the theme is web science meets network science. So I was thinking about then my group, we have students doing both. Okay, some students doing web structure mining. So this is part of web science. Some people are doing information network analysis. This is part of a network science. So of course, since I'm a data miner, so most of the work through the lens of data mining rather than a more general framework. But I'm going to show you, actually this is pretty exciting. Web science meets network science. Actually, in my group, not only they meet together, they discuss and collaborate together every day. Okay, so I'm going to show you why web science will meet network science is very necessary. The first thing is web, from the data miner point of view, web science is mining web structures, web contents. Okay, and network science point of view is, network. We are mining information networks. But why these two things really should get together? The first thing probably most people can realize is web itself actually is a gigantic, heterogeneous, unstructured, but it is a huge information network. Okay. Then if we do network science in a nice way, we probably can mine this web in a nice way. Then finally, we probably using the heterogeneous information network analysis, we can enhance the power of web analytics. So that's the general philosophy. Okay. Then I will just show you one case study, which is studied computer science research. Okay, because many of us, based on this morning's poll, many actually somewhat relate to computer science. Okay. And what I'm going to show you is one is computer science website. We actually confine to US computer science websites. We take DBRP, which is Computer Science Publication Bibliography Network. We'll see the web on computer science and how DBRP, these two things can be integrated together. Okay, and some interesting questions can be answered. For example, what are the popular, okay, let me see, what is this one going? Okay, so let me try to get this one done. I probably should cancel it. Maybe it's already canceled. So if you look at, for example, in Midwest, here we are. What are the popular research fields or subfields? Or some people may ask you, who are the leading researchers on XML or XQuery? How do the authoring web science collaborate and evolve? Okay. Whether those queries and all of the other queries can be answered automatically. I will show you actually all these queries. I cannot say all of them. For example, I will show you who is a search brand supervisor, okay, and what period of time. Okay, of course you probably know it, but we say we do it automatically just based on DBRP, and who are very similar to Chris's Falusas. Okay, and all these questions can be answered in a nice way. Okay, so I probably have to really get rid of this, otherwise. I just cannot, just, okay, yeah, okay, that's good. I'm not quite familiar with a Mac, okay, there you can see it. So I will first show you what I've been working on mining web structures. You probably think it could be interesting to link with web science, okay. The first thing is, can we automatically discover entity pages? This is actually UIC computer science. Okay. Then I'm going to show you that this one actually will be published in the Okay, sorry. Maybe. Okay. Sorry. I think maybe once I click, something popped up. Okay. Okay. That's good. Okay, thank you. Yeah, this one, yes. Oh, sorry, I should not click it. I think anytime I click this one, this pointer, it comes up. So I better avoid clicking the pointer. I better use fingers, okay? Okay, so I should stand close enough. This page is a UIC, computer science homepage, okay? Then suppose you get any single page, like this one is just my homepage. This is Tarek's. These are a bunch of professors' homepage. Okay. Whether I just give you one homepage, you can find all the professors precisely. Okay. Okay. Thank you. Okay. Sure. So whether you can find all the computer science pages. Okay. So if you think about any web structure, okay, almost in any institute, they have certain inherent structures. It simply says, this professor put it here, the other professor put there. It's not random. Actually, large information you based on this kind of arranged structure, you can discover automatically. Okay, that's nothing really magic. So we actually work out an algorithm. You tear this one, you go across multiple web pages. Actually, because the page, actually, sometimes you do not know where is the handle. You cross multiple pages, you go back and forth, you actually find the boundary, you can get it. Okay. The interesting thing you can get, I just show you one. This one actually is, for example, we took about 25 computer science, well-known computer science department. Just every computer science department will give one professor's homepage, try to get all the others, actually. If you look at this precision recall, it is not 100% just because the computer science faculty have some kind of magic. Everybody doing their own homepage. Some people even put their homepage using Facebook or LinkedIn as their homepage. So they are not really strictly following structures, but you can capture most of them. But if you look at UIC CS courses or CS research groups, you get 100% recall, 100% precision. You look at the US, like Congress, representatives, senators, different committees, you got 100%. We actually tried even for football. Okay, you give any one football player, actually you get all the 10,000 football player grab out. 100% recall, 100% precision. Actually, it's very structured. We tried Amazon.com and many other sites as well, but some are too big. Another interesting thing you probably can see is here. Okay, you get any, for example, this one is our Dan Ross homepage. Okay, you look at multiple paths. Actually, these paths itself is very telling. For example, you just look at the path labor. You actually can see this page is Dan Ross, who is CS faculty, is people, and this is department. Okay, but you go through the other one, you actually can see he's working on data mining. The other one could be machine learning, or natural language. You get different labs. You actually collect the major features just based on the path. Okay, so with this, you can do a lot of things. Another interesting thing is, because you grab all the pages, like we got 60 faculty, we grab all the pages. Okay. Then actually, based on this page, you do structural mining. Even they are all different. They construct by themselves. You actually can easily grab name, address, zip code, publications, collaborators. You grab a lot of structural information. Even they themselves try to make it unstructured because they just design web or play web by themselves. Okay. So with this, we are in the process of constructing one called WinX. WinX is Web Information Network Analysis for Computer Science. Okay. This one is in the middle because the due date actually is in June in Athens. It's Sigma conference demo. Currently, we work on both ends. One is work on the website, one work on the information network side. The remaining part, I'm going to show you the information network side, what things can contribute to this part. Okay. The information network side actually can contribute quite a lot. Okay. One thing I can show you is the major difference from many other things is many people are working on friends, link with friends, is co-author, link with co-authors. We're working on heterogeneous information networks in the sense one side could be conferences or terms or different papers. The other side could be authors. There are multiple entities that link together. Okay. With this, many interesting information can be mined. The first thing I want to show you is we got one is linking the clustering and ranking together. We discuss page rank a lot. Everybody thinks ranking is critical, which it is. But ranking without clustering, you're thinking about it this. You got all the computer science guys mixed together. You say, rank who's number one. Actually, it's pretty hard to rank. Which field is number one? It's still very hard to rank. Just because you mix the chicken and duck together, you rank them. If duck is bigger or chicken is bigger, or it's very hard to say. So in that sense, we say, if you want to do good ranking, you need to partition them. You do good clustering. And another interesting thing is clustering and ranking really should help each other. This is like a web science and network science. In the sense, you think about this. Okay, if you do cluster, okay, if the highly ranked one, for example, okay, we just put in Nashir or Tim, okay, if you say network science, you don't rank them high, probably things may change. Your whole structure may change. But you get first year PhD student publish one paper. You say, I rank this guy wrong. Okay, so what? Nothing really wrong. Okay, your whole structure, your whole cluster is still there, still in high quality. So missing one is not equivalent because not everybody is equally weighted. Okay, so based on this idea, we actually work out this rank class. The interesting thing is, of course, you probably say, how do you rank them? Okay. We just put some very simple rules. For example, we say highly ranked authors publish many papers in highly ranked conferences. But how do you know which conference is highly ranked? We say highly ranked conference attract many papers from many highly ranked authors. Okay, this one actually, this double many is very important because if your paper got rejected, you set your own conference. You just get your students get into the conference. That conference cannot be highly ranked. The reason is other highly ranked authors will not join you. Okay, you will not get this many. Okay, so with this one is collaboration. If you publish one with a very famous researcher, almost automatically you get it somehow boost up, which is naturally you can see if you co-author with Einstein, you could be a big scientist, right? So we built this one into our network rule. And it's interesting is after just a tiny few iterations, okay, this one actually is ranking, the ranking on different parts, different clusters, these different colors, is clearly separated. And the cluster after a few iterations is also clearly separated. If you look at the process from iteration 1 to 3, you actually can see the color start separating very clearly. So it simply says this ranking and clustering really help each other very, very nicely. Okay. And moreover, the other one I just show you is just two types. We call it bi-type network. Now, actually, we got into multiple types. We link as a star. The interesting thing is once you do clustering, the cluster, the small cluster is still a star. It's more like a DNA. When you chop some people into pieces, actually the DNA remain the same. Okay, that's the same thing here. The cluster remain the same. You have paper, you have venue, you have title, terms, and you have author. They all remain the same. I just show you one cluster. This is one actually is a database cluster. Why I call this one database cluster? You look at the term, the top ranked term. Database is system, data query system, management, object, relational. This is obviously this is database. You look at the conference, the highly ranked one, VRDB Sigma. You look at the authors, the highly ranked authors automatically also popped up. Okay, not only conference terms, author also popped up. Okay, we actually got into database field. We say who is really good on XML or XQuery. Those people pop up, and we go back to XML in database field. We check them. They say, oh, this is very good ranking. Okay, remember, this system has no knowledge of it. Of course, then we put in some knowledge. That means, what about we put in some training? Okay. The interesting thing is you put training on one class. With the link, they propagate to the other class. They propagate something in the middle. So this propagation across multiple types actually is very powerful. I just show you this one. Actually, is we look at many other, quite a few, classification on the network ones. And we show that once we get into this multi-typed network, if you look at the classification accuracy, sorry, I always forget this. Okay, this is one really, maybe I still should be able to. Okay, so it will take some time. Right? But if you look at this, you probably see that GNet mine actually, it is really much more accurate. The reason, obviously, is you use multiple networks. You probably see these are the terms on these several fields. We have database, data mining, AI, information retrieval. You look at top ranked terms, top 5 terms. It's almost probably the expert can get. Okay. And you look at the top 5 authors, and you look at the top 5 conferences. These are all automated. Okay. So it simply says this clustering, ranking, classification can integrate together. Okay. Another interesting thing I can show you is object resolution. Okay. You probably know the Chinese has lots of very short names. Okay. We pick a one which called Wei Wang. Okay. We found that that one was done in 2007. Wei Wang, there were 14 Wei Wangs. They share exactly the same last name, same first name. Okay. When the student told me, I said it's impossible to distinguish them because I myself actually co-author with 3 Wei Wangs. Okay. So, but the student did not give up. Okay. He actually drew this picture to me. He said it's possible because you look at the links. Okay. Look at links. Even I are co-author with the several Wei Wangs. They co-author with the other guys with rather different, extent. And also they work on different conferences or something. So with this, we actually work out an interesting one. We call this one called distinct. That means if you have different names, just based on the links and extensive study of the links, you actually can partition them nicely. The interesting thing is you do need training, but nobody wants to train 500,000 authors. How do you do it? We train by itself. We call self-boosting. What is self-boosting? Is we use the same set of data, the same DBRP data, 500,000 authors. We pick up automatically, the system pick up longer, unique names. We take this as a good example. Okay, we assume like Mike Stonemaker, there's only one in the world, or something like this. We pick up quite a good number of authors as the training set. We learn, we find the knives to cut different parts. Okay, then finally you probably can see this. This one actually shows there are, for example, there are 3 Hui Fangs. Actually, the accuracy, precision, both are 100%. Simply say we chop them very nicely because they work in different fields. We actually got Joe Hellerstein, who actually you can say who is a UC Berkeley professor, but there's another Joe Hellerstein actually in IBM research. They both are, actually there are 3 or 4 different Joe Hellersteins. Fortunately, they have different middle name. We actually took the middle name out and merged them, see whether the system can partition them back. Actually, you can see the precision is 100%. The recall is not because of several, we cannot distinguish them. There are several papers we dare not to partition. Okay. But overall, we went back to Wei Wang because Wei Wang, among all these cases, Wei Wang is still probably the most difficult case. Then we look at this Wei Wang, actually for 14 Wei Wangs, we recognize 13, we partition into 13 clusters. Okay. But the Shuni being Hampton, this Wei Wang actually got 2 papers eaten up, what disappeared. But if you just look at the papers, it's only 13 papers got wrong with 144 papers. So the link analysis does work. Another interesting thing I can show you is using links to do validation. Okay. For example, you go to internet, you say that there are different things people say differently. Okay. Which one is right? Okay. Of course, you may say if you sell products, it's very hard to say. But if you say news, most people probably trust those many news agencies. But which one, if I give you something, I say, I don't know, I got a conflicting answers. Can you figure out which one is the correct one? Okay. So originally, I also think this one is pretty hard-handed. Actually, I have some smart students. He gave me this example. Okay. This example just say, he gave a book called Rapid Contextual Design. Okay. I did not know this book. Okay. And he said, do you know who are the authors? I said, I don't know. But he said, go to the web. You look at those different providers, they give different author names. Okay. Which one is correct? Okay. Those are all book dealers. Of course, you know, of course, you go to Barnes & Noble, you really get the book, you look at it, there's only one is right, which actually is not Barnes & Noble, but it's A1. Barnes & Noble almost got it right, except the second author, the middle name was missing. Okay. But how can you judge which one is right? Okay. The interesting thing is you can construct an information network like this. Okay. This is the websites, these are facts, these are objects. If I give you this graph, I just say, just based on this graph, can you judge which one is right? You probably say, no way. Okay, just look at the graph, how can you judge it? Actually, this graph is very telling. Okay. And we actually work out some simple rules, then you go back to this graph, immediately you can judge it. Okay. This one, the first one, we say, suppose there's only one true fact. Of course, this is cut off a lot of things. You know, there are some ambiguous. For example, Obama, you know, based on different time, he played different roles. He could be a senator or you know, presidential candidate or presidential elect or finally become president. But we also assume, you know, these two, like Jennifer Widom and J. Widom, they are both right, but they have different degrees. They are linked together, have different degrees of accuracy. But the 3 and 4 are actually critical. 3 said the false facts of different websites are less likely to be the same or similar. It simply says this, okay. If you got, for example, a police catch 3 thieves who rob a bank, you think police will say, we got a panel discussion to see what happened? Never, okay. The police actually isolate them, question one by one. Why? Because they know if people lie, likely they lie differently, okay, in most cases. So police actually try to find this isolated case, which one becomes consistent, which one is really, you know, dispersed. So based on this, and also, of course, the last one is very obvious. If you keep telling lies, I trust you less. Okay. If you keep telling the truth, I trust you more. Then we go back to this one. You can figure out by yourself. You think about this. Okay. This O2, you look at this F4, will only provide by W2. But F1, this state facts, will provide by W1, W3, W4. Likely, okay, this F3 is the truth. This unlikely will be the truth. Based on this, actually, W1 gets some credit. So W1 predicted F1, but W2 predicted F2. W2 already got a penalty. Then you can say, likely F1 could be more trustable. Okay. With a large network, many, many assertions, you actually can do really good. For example, we took about 1,000 books, and we randomly pick up 100. We compete with Barnes & Noble. We pick up many, many websites, many book dealers. So you probably can see on every entry, we're actually better than Barnes & Noble on the accuracy. The reason, of course, we use Barnes & Noble as part of the answer as well, but we do not 100% trust it. We trust many of them. They vote. They use the network to do reasoning. Okay. So, and another interesting thing is with the network, you can do a lot of things. One is role discovery. If I show you this network, this is a very dirty communication network. Okay. And based on this network, can you figure out there could be a terrorist network, which this is the insurgent, this is their lead, this is the chief. Can you figure this out? You probably say, no way. But remember, okay, a normal insurgent, we're not directly communicating with this chief. Okay, that's the layers of communication. Even using communication is random, it is not. Okay, so based on this, we actually work out an interesting one is just based on DBRP data. Can you automatically determine who is whose supervisor, who's advisor at which years? Okay, so you think it's hard? Of course, you know, if you never publish with your advisor, it's very hard to distinguish. Okay, but most people do, right? So with this, we actually work out, you know, based on a few conflicting, you know, constraint rules they propagate. Actually, the accuracy, if you look at this, the accuracy actually is pretty high. With the finer one, with our optimized parameter, actually the accuracy reached 90%. Just give you a simple example, okay? For example, you say David Blake, who is his advisor? We actually work out two. One is Michael Jordan, one is John, this is CMU's Lafferty, okay? Then actually one is a PhD advisor, one is postdoc. Then the student actually pick up one of my students, Hong Chen, who is her advisor. Actually found two, one's Chang Yang, one's me. Actually, Chang Yang was his master advisor. Me, actually they got a year. The year is actually almost exactly right. And he picked up Serge Brand, say who is Serge Brand's advisor. And the system showed the number one is Monowani. Actually it's 97 to 98. Of course, after 98, he set up Google. He never really got a PhD defense. But at least it's an official advisor, which is true because he published many papers with Rajiv. So these shows you get all these networks. You can do a lot of very interesting things. Another thing I can show you is similarity search. Okay, if you use PageRank to do similarity search, most point out are the highly regarded one. Okay, for example. If you say, you got a PhD student, say, who is most similar to the student? You probably got some very big name. So say Tim Berners-Lee is probably most similar. You probably say the other side, say, no, I never know this guy. Okay, the reason is if you just look at the pointer, point two, you get a PageRank, you get highly authorized one, but it may not be the most similar one. Okay, so we work out the metapath based, okay. We actually, it's interesting is you think about this, you based on different paths, different network paths, you actually get a different kind of similarity. For example, we try Christos Valousis, okay. If you get APA, which actually is a co-author because they share the common paper, okay. APA, we actually got this several, Yuri is here. We got this several probably just based on the papers, how many papers co-authored substantially with Christos. Okay, these are the ones. But if you look at the co-conference, okay, the interesting thing is you look at co-conference. This is AP CPA. This is conference. You look at co-conference, it's a very different set. The reason is these people publish similar number of papers in the similar sets of conferences. So you actually can see the similarity. And we actually tried using the same network, try Flickr. Okay. Then we pick up a lotus flower and put it down here. You use different paths, you get different pictures. Okay. You probably see this path is no good. This path is too short. This is called ITI. You just based on tag. But people put tags sometimes randomly. Okay, you can see this bird definitely is not so similar with this lotus flower. Okay. But if you use this ITI, GITI, you also take the group label, group tag, not only individual tag, but also group tag. Then you probably see this one is automatically got it. This lotus flower, even this picture, has no similar color. It's not blossom for this lotus flower. You still see this is the top 5 most similar pictures. So you see the network, the path, actually with collective opinion can tell a lot of things. Okay. So what I should conclude is web science and network science, many ways can be linked together. This is what we are doing. Okay. We actually theoretically try to automatically get the web and mine this one and integrate anything in the real database. For example, DBRP is a real database. you integrate the web with the real database, there are lots of magic things can happen just because once you construct a network can infer itself. Okay, with lots of statistic collective behavior, things may happen. Okay, so that's what we see. Knowledge is power, but knowledge actually is on the web, but also is hidden in the structures and the massive links. So it really relies on us to mine it and finally get it out. Okay, so that's my talk. These are a bunch of papers from our lab. Actually, I put my book there, but the book, the third edition, is coming out, but they haven't given me the pictures yet. So I only put the second volume, second edition there. Last year we got one, 2010, got one book. This one is on link mining with Philip and Christos Faloussas. Collect lots of papers, including many of you actually contributing to this one. I think Lada, Yuri, lots of people contributing chapters to this book. Okay, so I'm done. Thank you.
Are there any questions you'd like to ask? Jiawei?
Sorry, it may take some time, maybe just 30 minutes, right? So it's not that long. Okay. Okay, any questions? Yes? Bashir?
I have a question, very profound question. Did the Weiwangs collaborate with each other?
Oh yeah, that's a good question. Actually, fortunately, Weiwang never collaborate each other. Even she collaborated with many. I mean, the most productive Weiwang collaborated with many, but actually they collaborated with somebody with Wang, but never collaborated with the same name. Otherwise, you never can recognize it. Okay. Okay. Thank you.
Thank you very much.
Thank you.